In this lesson, we're going to talk a little bit more about understanding the complete path or process associated with the data path and microprocessor implementation and design. And so previously, we reviewed concepts related to how a clock signal is measured and affected and associated with our instructions. We took a look at the register construction and how it's utilized. We've introduced the concept of a register file. We took a look at various components associated with memory as well as DRAM and SRAM, and also took a look at the structure of the arithmetic logic unit that is within a processor. And so now let's continue by focusing our attention on understanding the elements that are associated with the data path. And it's important to keep in mind that a data path will consist of all of the functional units of the processor that are required to execute a set of instructions. We have our specific elements that hold data, and within the data path here, we have a construction that represents at a high level different elements that interact together. We have our program counter, we have memory, we have the instruction register, we have our register file, and then we also have our ALU. And the ALU and other things such as adders are the components that are utilized to operate on memory. So we can take a look at specific data paths that are associated with various instructions, and we will start out with a generalized example. It's important to keep in mind that this architecture is used to provide for a path for building various data paths based off of different instructions that can be executed. And so now let's consider our example of how data path is executed. And when we deconstruct this representation, we're going to take a look at how an add instruction would propagate through our processor. In this consideration, we'll use the add instruction of the LC2200 that we've been working with. And so the first step that needs to occur with this data path execution is that we'll need to use the program counter to specify the memory of the location that contains our instruction. And so our program counter is going to enable us to pull that instruction from memory based off of the memory address associated with it. Once we've been able to read the instruction from memory, we need to store it into the instruction register. And so this is important because it provides for a basic understanding of how the data will propagate through the system. Once the instruction is available in the instruction register, then we need to use the register numbers that are specified by that instruction. We need to use those provided numbers so that we can read appropriately the registers that contain the values that are needed from the register file. And what we can see in this example here is that we have a dual ported register file. And so once we have the appropriate address of those registers, the ALU is utilized in order to perform the appropriate arithmetic operation and calculations. And so that will propagate through our system and appropriately the result will be stored in our register file. So these are a few steps that are required in order for the execution of our add instruction. So now let's kind of take a look, or at a high level think what is needed in order to determine how many clock cycles are required for these instructions to execute. And the instructions that are executed are: the data path is from the program counter to memory to the instruction register, the register file to the ALU, and then stored back into the register file. So exactly how many cycles does it take for these instructions to execute successively? It's important to keep in mind that all of the storage elements except for memory are going to be positive edge triggered. And so what this means is that it'll take one clock cycle in order for us to transfer information from one storage element to another. And so this can be done, of course, through a different connection of logical components. As long as the clock signal is long enough to account for any type of propagation delays and latencies, then it can occur within that clock cycle. And so let's kind of break down the various steps that are required so we can see, will this execute in one clock cycle for all 1, 2, 3, 4, 5, 6, 7 of these elements? Will it be 2 clock cycles, 3, 4, 5, or none of the above? And so what is the path that is utilized? So let's take into consideration that we can consider that we have essentially 2 steps associated here. And what does this mean? So if we can consider that the initial steps where we go from the program counter to memory to the instruction register are essentially going to take place within 1 step or 2 steps. This results in the write to the instruction register being a rising edge. And then we have to consider what occurs within step 3, where we read from the register file to the ALU and then write back to the register file. What are some factors that determine how many clock cycles this is required to take? Well, essentially what we're able to deduce is that this can occur in 2 clock cycles. So we can break this down into our 2 steps, into 3 steps that are associated with the complete data path. And so this means that from the PC to memory to writing to the instruction register can occur in our first clock cycle. And then our second clock cycle is going to entail us reading from our register file to doing our ALU computation and then writing back to our register file. And so steps 1 and 2 are completed in one clock cycle, and step 3 is done in an additional clock cycle. Essentially, the, the, the output of the IR is going to occur at the beginning of the second clock cycle. And so how do we decide how long a clock cycle is? Well, there are a number of different factors that come into play. So let's assume that we have our register here, and what we need to do is determine how long we'll need to hold the clock edge. And this isn't necessarily going to be represented by ones and zero. They're going to be represented as voltages, since we're taking into consideration the components required to implement our registers and ALUs. And so whenever you get into working with voltage components, you have to consider delays associated with the materials used to create them. And so it requires a understanding of a little bit of electronics that is beyond the scope of this course, as we're computer scientists. But it's important for us to be aware that these devices are associated with physical constraints, and these physical constraints can result in delays, propagation time delays, and latency factors. And so the materials that we use, silicon for creating chips and various other components, they are essentially limited by the laws of physics. And when we think about that, everything kind of relates back when we talk about computing to the speed of light in terms of how fast and how efficient things can be. And so that's why it's easier to note that the smaller the smaller the chip is, the quicker we're able to accomplish calculations and minimize delays, of course. And so this goes into a question that we have, in that we've determined that it takes 2 clock cycles for this data path to complete. But how do we know how long a clock cycle should last, or how long it should be? And so what do we do? Should we ask Intel or Apple? Is it just by magic that we determine it? Do we add up all of the data path delays? Or do we make an assumption and set it arbitrarily and hope that it works out? Take a second to think about what might be the most logical answer. How is the clock cycle determined based off of our data path? Well, in order for us to determine how wide the clock cycle is going to be, essentially we're going to have to base it off of adding up the elements that are associated with our data path. And that includes the appropriate delays that might occur. And so essentially, let's kind of take a look at how the instructions break down within our data path here again. We have our 2 steps that go from the program counter to memory to the instruction register. And then we have from the instruction register to our register file. We do our add in our ALU, and then the resultant is written back to the register file. And so considering these paths, there are different factors that come into play. And when we talk about these, there are specific parameters that can be associated with the system that we need to take into account, because there's going to be a potential for delay that is going to be associated with all of these components. And we need to measure which path is going to have the longest delay. And so in order for us to be able to determine that, we need to analyze a number of different components and factors that can affect the width of our clock cycle. And so these are different factors that can be such as the time that it takes for the output of the PC to be stable for reading. It can be the result of it can also be based off of the write delay for the address required to propagate from the output of the program counter to the address input of memory. It can be access time of the memory to read the address location. It could be based off of wire delay for the value read from memory, and then that needs to propagate to the input of our instruction register. And then it can be the time that has to elapse for the input of our instruction register to be stable before the second rising edge. And so with all of these are just a high-level overview of some typical factors that we have to consider when we're trying to determine appropriate width of our clock cycle. And so going back to our example, we need to determine which data path is going to have the maximum width. And that isn't necessarily just associated with how long the path is, but it's the combination of the delays of each of the elements, which isn't necessarily represented here in the diagram. And so if we were to consider that for our existing diagram, we need to take into consider the delays for the PC, the program counter output to become stable, the delay from the program counter to the address of memory, the delay of the memory to read, the delay for memory to write to the instruction register, the delay for us to set up the instruction register, and the delay associated with holding the instruction register. But then we also need to consider for step 3, appropriate delay components. And that can consist of the delay that is required for us to write from the instruction register to the register file. And then we also have what it takes for us to read from the register file. And we also have to consider the delay from the register file to the input of the ALU after it's been read. And then we also need to consider the delay from the ALU back to the output of the register file, and then the time that it's going to take to write the new address to the register file. And so taking these into consideration, the maximum of these two components will result in our clock width. And so for steps, based off of the table that we've utilized here, step 1 results in the delay of 2060 picoseconds, while step 3, which is our operations here, reading from our register file to the ALU back to writing to the register file, is going to take 1,850 picoseconds based off of these measurements that we have for each one of these delays. And so our maximum the clock cycle width that we are going to utilize is going to be the max associated with steps 1 and 2 of 2060 picoseconds. And so that means that we have two, um, two clock cycles that are associated with that. And so these are some factors that we have to consider in order for us to analyze the type of connections that are needed. And so in order to further understand these components, we need to be sure to consider factors that affect the memory to register file input and how these connections of the elements are executed. And so there are various components that we have to consider, and those are what we've said. So we have to consider memory to register file input, register file output, our ALU output to our program counter, instruction register to ALU in to carry appropriate offsets. And basically this can result in a lot of wires and additional delays that make things hard to calculate and determine. And so what can we do in order to minimize the number of calculations that we would need to do to determine our clock cycle? Well, we have a solution for that, and that is what leads us towards the idea of a bus to provide for a shared connection across multiple components. And so a bus is going to basically allow for a electrically conductive path for data to be transmitted inside our chips and our computer system. And so a conventional bus is going to consist of a number of parallel conductors, and that can be conventional wires. It could be copper. It could be utilized via aluminum trails, a printed circuit board, but it provides for a communication channel that can enable shared transmission. It's important to note that for the bus to be utilized, it is only allowed for one transmission at a time. And so if you have a bus that is going to be communicating between various components, then that is going to be a system bus. And so here we have a representation of what we call a single bus. And so in this case, we have one bus structure that's going to be used to communicate between the functional elements of our system. So that can be for our microprocessor, as well as other available peripherals. And so here we have a representation of a single bus that results in all of the wires essentially being shared, which means that there's only one type of communication that can occur at one time. You also notice that we have our elements here, or these triangular elements that are used to represent the output of the data path onto the bus. And these are what we call drivers, and they can also be referred to as tri-state buffers as well. And so using our drivers, we're able to isolate appropriate elements from our data path from the bus. This represents a single bus design, but we're also able to utilize a dual bus or two bus design as well that can allow for multiple communications to occur. And so in this example here, we see that we have first represented that we have a dual ported register file. So this enables us to read and write, read two addresses and supply it to the ALU in the same clock cycle. But in order to accomplish this, we need to have two buses in order to provide for the dual communication. So we have the red line representing one bus and the purple representing the second bus. And these are able to carry out the data values and addresses needed for each clock cycle. And so most importantly, the red bus can be utilized to carry the values of addresses, and the purple bus is used to represent how data is carried from one system component to the next. And so in this representation, we can see how our initial step 1 and 2 instructions can be accomplished in one clock cycle using a dual approach, where we're able to write the address for the red and the data for our purple using our purple bus. For step 3 of our instruction, we're able to also accomplish the same step using our dual bus approach as well. And so essentially this allows for addresses and data to be written by utilizing both buses. Now, does this cause a change in the number of clock cycles that we need to execute? So let's take into consideration how this is executed. We can consider that it's going to be done in 2 clock cycles again. And why is that? Let's analyze how each step occurs. So first, for the first clock cycle, we have the program counter to the red bus. And so when the red bus is being used by the program counter, this means that no other component can make use of the red bus. Next, we have the red bus to the address of memory. Memory then reads the location specified by addressR. And so the data from the out is going to then be used on the purple bus. And also note that during this cycle, no other component can use the purple bus at this time. And then the purple bus is transferring the data to our instruction register. For our second cycle, we have our instruction register that register will supply register numbers to our register file. Next, we'll need to read the register file and pull out the data from the 2 source registers. The register file will supply the data values from these 2 source registers to our ALU. The ALU will perform our add operation, and that resultant is transmitted via the purple bus to our register file. The register file and the destination register are then provided to our instruction register. We can utilize a single bus approach and incorporate a memory address register in order to copy our address from the program counter as well. And so with this, we can have the memory address register that can store the memory address from which the data will be fetched to the CPU. It's important to keep in mind that the memory address register is going to hold the memory location of the data that needs to be accessed. So what we want to be sure to keep in mind is that the benefit of this approach is that we don't have to run dedicated wires connecting every pair of data elements by using the two shared bus approach. And so in this, we have covered our appropriate logic design review, as well as provided for a few examples to represent the data path of our system.